Hi everyone, thanks for watching. My name is Deanna C. I'm a postdoc currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And today I want to talk to you about cosmological constraints on the number and masses of neutrinos. So basically how we can constrain or study neutrinos using cosmology. And this is a topic that I really like because I feel like it really draws on both particle physics and cosmology, and it shows the interdisciplinary nature of neutrino physics. So jumping straight in, we know by now that massive neutrinos are part of the standard model of particle physics. Now, before we didn't know that neutrinos had masses, but thanks to neutrino oscillation experiments, we've been able to see that neutrinos change flavor and therefore they must have non-zero mass. From this perspective, from a particle physics point of view, there are several things we can constrain or study in terms of neutrinos. We have 3 mixing angles, which is related to how the flavors mix together, and we have 2 mass squared splittings, which is the relative difference between the different masses. While we try to constrain the masses of neutrinos, the overall scale, the absolute scale of the neutrino masses, so the sum of the 3 masses of neutrinos, is currently unknown. We have lower theoretical bounds from a particle physics perspective. This comes in the form of normal hierarchy or inverted hierarchy. So this is related to whether we have 2 massive and 1 light neutrino or 2 light and 1 massive neutrinos. In the case of normal hierarchy, we have a lower theoretical bound of the sum of neutrino masses larger than 0.06 electron volts, while in the case of inverted hierarchy, this lower theoretical bound is 0.1 electron volts. So this is what we know from particle physics. But I'm not a particle physicist, I'm a cosmologist, so let's talk about the history of the universe. Now here I'm showing a sketch of the history of the universe. Past is on the left, present day is on the right. And what I'm showing here is the relative density of different species normalized to the total density in the universe, so to the critical density today. And what you can see here is we have photons, neutrinos, cold dark matter, baryons, and dark energy. In the early universe, photons and neutrinos were the 2 main species. Photons were more abundant than neutrinos, but they were both there. And just to mention that here I am showing the case of neutrinos with the total mass sum of 0.3 electron volts, just to show the example. Now, what I really want to highlight here is that neutrinos play a role throughout the history of the universe. Photons start very abundant, but at some point this gradually drops away and they barely contribute to the energy density today. This is because at some point we switched between the universe being radiation dominated to matter dominated, so photons diluted away quicker than massive species. Neutrinos, however, undergo a transition from being relativistic to non-relativistic. This means that in the early universe, neutrinos behave as radiation, but later on in the universe, at this time after this transition to non-relativistic, they behave as a massive component. You can see here several key points marked. There is BBN, this is Big Bang nucleosynthesis. This is when the first elements were formed. And at this point, neutrinos and photons were both key components in the universe, so they're going to play a role in Big Bang nucleosynthesis. Later on, at the time of CMB, when photons broke away from normal matter, or from the rest of matter, from baryonic matter, we can see that neutrinos, photons, dark matter, and baryons all play a role. And then, of course, later on in the universe, dark energy becomes a dominant component, but neutrinos do not disappear completely. Today, neutrinos account for about 0.5% of the matter content of the observable universe. So they really are a key component, both in the early universe and the late stages and today. So these neutrinos that were very abundant in the early universe experience a decoupling in the same way as the photons that make up the cosmic microwave background radiation broke away about 380,000 years after the Big Bang. Within the first few minutes after the Big Bang, we also had the decoupling of neutrinos. This was when the universe was at a temperature of about 1 MeV. At this point, neutrinos decoupled from the rest of the standard model and have been kind of doing their own thing ever since. Today, they make up the cosmic neutrino background, which has an average temperature of 1.9 degrees Kelvin. Today, there are about 340 neutrinos per cubic centimeter in the universe. So neutrinos really are still abundant. Ideally, someday we will actually measure this cosmic neutrino background, but that is something that is still quite far away from where we are right now. So the density of massive neutrinos today is very much related to the sum of total neutrino masses. So you can see here we have the relic density of neutrinos today normalized with the Hubble constant, because that's just how we like expressing our densities. And then we have the sum of neutrino masses here. This number, this 93.12 electron volts, is a fudge factor, just related to what we know about how neutrinos behave in the universe. Another thing that is relevant for cosmology is the neutrino energy density. Now, the energy density of neutrinos is going to be related to the energy density of photons. good thing is that the energy density of photons is something that is well known. It's something we can measure from the CMB. So this is a number that we actually know. And then we have this N effective parameter here. This is the effective number of neutrino species. So basically, this tells us how much radiation or how many relativistic components there are in the universe, except for photons. So this counts neutrinos and other massless or light relics. And it is normalized to the energy density of one neutrino family. So you might think that if there are 3 neutrinos, this is going to be very close to 3. And it is very close to 3, but N effective is defined in the case of an instantaneous decoupling, whereas neutrinos do not decouple instantaneously. The fact that there is this gradual decoupling of neutrinos, and there are several different effects at play here, means that the actual effective number of neutrinos is slightly larger than 3. Currently, theoretical calculations put this at about 3.044. So we have a very good theoretical prediction, or very accurate theoretical prediction for what we expect the effective number of neutrino species to be. So at the end of the day, cosmology is going to be sensitive to 2 total things, or 2 properties of neutrinos. The sum of neutrino masses, mu. Just comment on notations throughout this talk. Anytime I use capital mu, I'm referring to the sum of total neutrino masses, so all of the 3 neutrinos added together. And cosmology is sensitive to NF, so the total number of neutrino species. This is something that we can constrain at the time of Big Bang nucleosynthesis at CMB times today. So this is something that is also going to be a property that we're interested in constraining from cosmology. So now I want to talk about how exactly neutrinos impact different aspects of cosmological evolution and different things happening inside the universe. Now I'm going to divide these effects into background effects and perturbation effects. Background effects are those that are going to impact the overall background evolution of the universe, while the perturbation effects are more focused on how the actual neutrino perturbations interact with other perturbations or perturbations of other components in the universe. Focusing first on the background effects, in the early universe, neutrinos are a relativistic component. They contribute to the overall amount of radiation the overall amount of radiation in the early universe, and this is going to affect the early expansion rate of the universe. At some point later on, neutrinos will undergo this transition from relativistic to non-relativistic. This means they go from behaving as radiation to behaving as matter. When this happens, it is going to have an impact on the overall gravitational potential of the universe, and this is going to be something we can notice in the form of the early integrated Sax-Wolf effect. At late times, neutrinos behave as matter, so they will affect the evolution of the universe or the expansion rate of the universe as any other matter component would. Now moving on to the perturbation effects. Neutrinos are going to have smoother perturbations than other components such as dark matter. This means that neutrinos are going to slow down early dark matter clustering. There's also going to be some coupling between the neutrino perturbations and the photon perturbations. This is going to become significant, especially at CMB times, where the perturbations of the neutrinos are going to be slightly faster, or they have faster velocity dispersion than photons. This means that the neutrinos are going to have a drag effect on the photons, and this is something that we will see in CMB, in the cosmic microwave background radiation. Now, at late times, neutrinos are once again going to slow down dark matter clustering, but also normal matter clustering. This means that the overall amount of neutrinos in the universe is going to impact the amount of structures that we have today, because neutrinos do really impact how other species can cluster in the universe. So here we see background effects at the top, perturbation effects at the bottom, throughout the history of the universe, and later on I'm going to come back to this distinction of background and perturbation effects. But overall, what you can see here is that neutrinos really do impact a lot of different aspects of cosmology, which means that cosmology is really an ideal probe to studying neutrino physics. However, I just want to make some caveats that there are several limitations towards studying neutrinos with cosmology. Some of these are ones that we can overcome, hopefully, in the future, and some of them are just due to how neutrinos behave in the history of the universe. Now, the first thing is that the neutrino mass depends on the cosmological model. So everything I'm going to discuss in this talk is going to be under the assumption of the standard cosmological model, so lambda CDM. However, you can relax all of the bounds that I'm going to discuss here by going to different models, which we're going to see in other talks at the Neutrino from Home conference. So I'm going to focus purely on lambda CDM. I also want to add the caveat here that this model dependence is being mitigated somewhat now because we're getting many different probes of neutrino physics. We're getting information coming from many different aspects. This means that the overall constraints that we're getting are becoming more robust to the underlying model. Once we have information from many different probes, there are lots of different constraints that play a role, and then the different cosmological models become harder to play about with. So this model dependence is somewhat being mitigated, but there is still a model dependence of all of the constraints I'm going to discuss here. Another point is that cosmology cannot probe the overall hierarchy. So the cosmological probes I'm going to talk about are insensitive to whether we have normal hierarchy or inverted hierarchy. On the other hand, this is a good thing because it means we can treat the neutrinos as 3D generative components. So we can treat the neutrinos as having the same mass. In terms of cosmology, the overall impact is really just on the total sum of neutrino masses, not the individual masses. Finally, there's one thing we need to be aware of, and that is that in order to study neutrinos, especially at late times when we're talking about structure formation, we're going to have to deal with the nonlinear structure formation effects because neutrinos are going to play a role at late times. What you can see here on the right-hand side is the matter-power spectrum, and I'm showing 4 cases. I'm showing 2 cases with massless neutrinos and 2 cases with massive neutrinos. And for one, I'm showing the linear and the nonlinear. So the solid lines are when we include the nonlinear effects computed with HM code, and the dashed lines is what would happen if we only focus on the linear matter-power spectrum. 2 different masses here, 0 mass and 0.3 electron volts, sum of total neutrino masses. And you can really see that if we ignore the nonlinearities, we very much underestimate the matter-power spectrum on small scales. So this is something we are going to have to deal with as well. But overall, cosmology is going to provide a very good way of constraining neutrino physics, just bearing in mind these caveats. So how do we go about studying neutrinos from cosmology? I already mentioned before that neutrinos are going to have a significant impact on the cosmic microwave background radiation. Also, we're cosmologists, we have to include the CMB in everything we do. So the cosmic microwave background radiation provides a snapshot of the early universe. It is this map of the photons that decoupled around 380,000 years after the Big Bang. We can look at 3 or 4 main components. We have the temperature anisotropies, which are the ones you see here in the top right. We have the E-mode polarization, bottom right. We have the cross-correlation between E-mode and temperature, which is middle at the bottom. Potentially, we could also measure B-mode polarization, although that is something that is quite hard to constrain from the CMB alone for now, but there will be constraints on that in the future. And then we have the lensing spectrum, which is related to how the CMB photons are lensed. So these are the main components that were included in the Planck analysis, which is what you can see here. And I'm mainly going to be focusing on the temperature anisotropies here. So now what I want to do is talk about the 2 main things that we can study in terms of neutrino physics, which was the effective number of neutrino species and the total mass of neutrinos. And I want to talk about how these 2 different parameters impact the CMB. So first, in terms of the total number of relativistic species, so N effective, I'm going to focus here on delta N effective. So this is where we take the standard value, 3.044, and then we increase it or decrease it with a certain amount, which is going to be our delta N effective. So I'm showing first the impact on the temperature spectrum. So I've got the ratio here of a model where we vary delta N effective compared to the case where we have N effective of 3.044. And I'm showing 4 different cases. The first one is where we decrease delta N effective. So we add a delta N effective of minus 0.5. And then 3 cases where we increase this by 0.5, 1, and 1.5. So this means that we're looking at the cases where we have, for an example, 3.544 effective neutrinos. Now, the one that I'm showing here, you can see there's a lot of effects. It seems like adding or changing this N effective really does modify a lot of different things in terms of the CMB. However, there is a choice to be made here, and that is what parameters we keep fixed when we increase N effective. Now, the case that I'm showing here, I have kept fixed the cold dark matter, so the density of cold dark matter. I have kept fixed the Hubble parameter. By doing this, we actually change the redshift of equality, so the time of equality shifts to compensate for this extra species that we've added in the early universe. Now, this is something that is a bit misleading because the redshift of equality is something that is pretty well constrained from CMB physics. So it would actually make more sense to keep Z equality fixed and reabsorb some of these effects by modifying other parameters instead. So what we basically do here is we absorb the background effects, the ones that I mentioned before, that really play a role in the evolution of the universe. These can be reabsorbed in terms of by adjusting the amount of dark matter and H. So I just want to show the more realistic case here, or the more illustrative case here on the bottom right. Now, what I've done here is I've kept fixed the redshift of equality, and I've modified omega CDM, so the relic abundance of dark matter, and the Hubble parameter in order to maintain that equality. So by doing this, we really absorb some of the background effects into these other parameters. By doing this, we can really separate out the perturbation effects of neutrinos. And you see that by increasing N effective or decreasing N effective, we have effects, especially at late times, but at early times, we have a bit more integrated Sakharov effect, but then at late times is where we really see the impact. One reason to do this change and present it in this way is that then you can really see that there is a connection between N effective and the Hubble rate. By increasing one, and we can absorb the effects of increasing one in the other. This means that these two are going to be degenerate. And this might be interesting if you want to do anything like solving the Hubble tension. It's important to bear in mind that N effective does play a role in this parameter as well. Now, in terms of the sum of neutrino masses, these behave as both relativistic in the early universe and non-relativistic later on. This means we're going to have different impacts on the CMB spectra, depending on whether the neutrinos are relativistic or non-relativistic at the time of CMB decoupling, at the time of photon decoupling. And this will depend on the mass. So here I'm showing two spectra. I'm showing the temperature one and the lensing one for different masses. And this is always normalized with respect to a case where we have zero masses. Once again, here I have fixed omega CDM and H. This does mean that I'm shifting the redshift of equality. And this could be reabsorbed in a shift of parameters like I showed before. However, this is going to change slightly depending on the masses of neutrinos, because if neutrinos are still relativistic at the time of decoupling, you have to take into account the redshift of equality between matter and radiation. Otherwise, you have to take into account the redshift between matter, the redshift of equality between matter and dark energy. So you could also reabsorb the background effects, but here I'm showing both background effects and perturbation effects together. We can see that in terms of the temperature spectrum, we have this overall shifting and the shifting of the peaks, which leads to these oscillations. But importantly, in terms of the lensing spectra, we have an overall suppression as we increase the neutrino masses. And we'll see later when I show the actual constraints that the biggest constraining power from the CMB itself does actually come from the lensing spectrum. What really adds to it, temperature anisotropies and the polarization anisotropies can constrain the sum of neutrino masses, but lensing really adds this extra thing to it. So all of this up till now was in terms of the CMB anisotropies. We focus on temperature anisotropies and lensing anisotropies. But as I mentioned earlier, neutrinos are also going to impact the growth of structures. So I want to illustrate this by looking at these two images here. Now, these simulations are quite old, but I think they're very illustrative. They're very cool to see side by side. So what you can see here is a slice to an n-body simulation, simulating the overall structure formation in the universe. On the left, we have very massive neutrinos. This value is slightly high. It's just been chosen representatively. And on the right, we have the case of massless neutrinos, so where we have no mass. And the different colors here denote the different overall density, blue being very underdense and red being very overdense. In the case of massless neutrinos, you can see that there are a lot of bigger structures and not many smaller structures, so the density contrast is substantially bigger. The voids are much emptier and the dense regions are much more full than when we compare to the left image where we have neutrinos with mass. Now, the reason for this is because the neutrinos, the massive neutrinos, are going to slow down the growth of structures. They're going to slow down clustering overall. So when you don't have massive neutrinos, clustering happens very quickly. The gravitational potential is very big. The gravitational wells are substantially bigger. However, in the case of massive neutrinos, this is mitigated somewhat. The neutrinos kind of wash this out. They unify everything. So they actually slow down the formation of structures. This means that you don't have these overdense and underdense regions that you do in the case of massless neutrinos. So this shows that studying the matter-power spectrum really is going to help us constrain the sum of neutrino masses. So like before, I want to start by focusing on N effective. Now, increasing these relativistic species is going to affect the overall matter distribution. Like before, I'm showing the ratio of matter-power spectra, focusing on a case where we vary N effective compared to a case where we have fixed N effective of 3.044 with different delta N effective values. As before, in the top, the figure I'm showing right now is where we fix omega CDM and we fix H, which means we are changing the redshift of equality. As before, I want to reabsorb the background effects by shifting other parameters and really focus on the perturbation effects. If we do this, I maintain the redshift of equality fixed by absorbing some of the impact of the neutrino physics in changing omega CDM and H. And now you can really see that the impact of N effective becomes dominant at small scales, where if we increase N effective, we increase the overall matter-power spectrum. If we decrease N effective, we go below it. So this is really the impact of just adding relativistic species in the universe. This is for now considering non-massive, just N effective. But again, you can see the importance of absorbing these background effects in order to really highlight the perturbation effects. Finally, we can look at the impact of the sum of neutrino masses on the matter power spectrum. And here, I'm focusing on the case where we're fixing omega CDM, we're fixing H, and just shifting the redshift of equality. This could once again be reabsorbed in a shift of parameters, but in terms of the matter power spectrum, it is quite illustrative to just look at it like this. And we can see the main impact of increasing the neutrino mass is to reduce the growth rate. So we damp small scale structures. Small scale structures have this damping. This means that massive neutrinos do erase structures on small scales. So by focusing on small scale structure, we really can hope to constrain neutrino masses as we go to smaller structures. This might be easier to constrain. So this is the figure that we often show, even though, as mentioned before, we could reabsorb some of these effects. It really is illustrative here to show the sum of neutrino masses suppressing the formation of structures. So the next question, of course, is how do we measure the matter power spectrum? Of course, when we're talking about the cosmic microwave background radiation, we know what we're measuring is the CMB. Whereas in terms of the matter power spectrum, there are many different observables that can actually help us constrain the matter power spectrum. This figure here is a summary of the constraints that we had in 2018. This figure is part of the Planck collaboration, the Planck paper releases. But you can really see here that we have CMB constraints on some scales. We have probes like SDSS, we have BOSS measuring the Lyman alpha flowers, we have cosmic shear, re-cleansing experiments with dark energy survey. So I want to just talk individually about these probes and explain how these different probes help us constrain different aspects of the matter power spectrum and therefore neutrino masses. And the reason I want to do this is because it will really highlight the advances we can expect in the next few years in terms of constraining neutrinos from cosmology. So the first probe of the matter power spectrum I want to talk about are baryon acoustic oscillations. Now, baryon acoustic oscillations are caused by the interplay between matter and radiation in the early universe. You have matter causing a gravitational force pulling things inwards. You have radiation causing pressure pushing things outwards. So you have these oscillations. This is going to leave an imprint in the overall density field. So you're going to have overdense regions and overdense regions corresponding to these waves. Once the CMB photons break away, this radiation and matter balance no longer needs to be kept. Radiation breaks away, and these sound pressure waves stop. But the final size is imprinted within the universe today. So this is what we call the sound horizon, and this is something that can be measured by looking at the overall distance between galaxies. Now, the average distance between galaxies is going to be very, very spread out, but there is going to be a number that is going to appear many more times than others, and this is going to be this initial sound wave, the diameter of these sound waves. And of course, what you can see here in this figure is an illustration, an artist's impression. What you'd actually have is billions of these overlapping circles. So you don't directly see these bubbles of the acoustic waves in the universe, but this is a number that you can pull out more often in galaxy survey. So if you measure enough galaxies, you can actually reconstruct this sound horizon. And this is something that we can do with galaxy maps. For example, the one produced very recently by the Dark Energy Spectroscopic Instrument. You can see their amazing galaxy map down here in the bottom right. And from here, you can pull out the BAO scale. And I'm not going to talk too much about DISY results because there will be a talk about DISY at the conference, but I just think this is a very pretty map. Another way we can study the matter power spectrum is by using hydrogen clouds in the universe. Now, we're talking here about hydrogen clouds between galaxies, or just the overall hydrogen in the universe, which there is a lot of. One probe that we have towards this is Lyman alpha flowers. Now, Lyman alpha flowers is what you get when you look at the light coming from a distant quasar. On its path towards us, this light is going to be absorbed by the hydrogen clouds in between galaxies. This is going to cause a series of emission and absorption lines in the spectra of the galaxies, in the spectra of the light coming from these quasars. So by the time the light reaches us, we have this mess that you can see here on the right. Lyman alpha flowers is trying to use this to map the hydrogen clouds and therefore the underlying matter distribution in the universe. Another probe that we have for hydrogen is the 21 centimeter line, where we're trying to look at a specific transition that takes place with hydrogen atoms that we know lies at the 21 centimeter line. So this is what we can achieve with radio astronomy. And this is something we are hoping to measure in the future. Moving to slightly smaller scales, so things that are closer to us. In the late universe, structural growth can be measured by weak lensing experiments. So here we're looking at how much light is distorted due to gravitational objects. We can do this by looking at, for an example, cosmic shear. cosmic shear is how much galaxies are distorted due to this gravitational lensing. There's this very cool illustration that was put out to help explain the dark energy survey results, where you can see what a sheared sheet would look like. And we don't actually mean sheared in terms of the wall here, but actually sheared in terms of distorted and the blending and the noise. But the idea of weak lensing experiments is to try to reconstruct the original galaxies based on what we see. And by measuring the amount of distortion or the amount of shearing that we have here, we can get an idea of how much matter is between us and these galaxies. And this allows us to reconstruct the matter-power spectrum on really, really small scales. So you can see there's a lot of different ways we can go about trying to measure the matter-power spectrum. So putting it all together, we have a lot of experiments that can measure the matter-power spectrum. And of course, we have cosmic microwave background, which is going to measure the photons that decoupled. As I've explained, both of these are very sensitive to neutrino physics. So we can really put together a lot of different things to try to study the sum of neutrino masses and n effective. So first of all, let's focus on the bounds that we have on n effective, so on the overall relativistic components in the universe. And I'm going to show the bounds from Planck, and this is first going to be Planck using temperature and polarization anisotropies. This is shown in red in the figure here. And then I'm going to move on to Planck with BAO and lensing, which is shown in blue here. So when we just consider Planck polarization and temperature anisotropies, we get a bound on n effective of 2.92 plus minus 0.37. This is, as you can see, very close to 3, so it is a pretty good constraint. Once we add lensing and BAO into it, this becomes 2.99 plus minus 0.34 or 0.33. So these are very, very close to 3, which is very good because it's very close to the theoretical prediction. But I just want to focus on the constraint that we have here in the figure. So this is from the Planck paper. In the red and blue contours, you can see the 1 and 2 sigma preferred regions by Planck and Planck plus BAO and lensing respectively. And this is showing NF as a function of the baryon density. But I just want to focus on the gray, blue, and green bands here. So these are the different bounds or constraints we get from Big Bang nucleosynthesis, which, as I mentioned before, is this time where we form the primordial elements in the very, very early universe, where neutrinos and protons played a big role. So in gray here, you can see the constraints we have on helium abundance, whereas in green and blue, we have the constraints on deuterium. The difference between the green and blue bands are just depending on how you measure deuterium. These constraints have improved since then by measurements, for example, by Luna, but they're not included in this figure, but these bands have improved. And the bands are now very close to the green ones here. But what I really want to emphasize here is that you have the helium band in gray, and then you have the deuterium band in green and blue. And you can see that where these two overlap is also where the Planck contours are. And this is something that is really a good kind of proof that we're on the right track, that our standard model of cosmology makes sense. Because the bounds that we get from Big Bang nucleosynthesis really do overlap with the bounds we get from CMB physics. So these contours did not have to lie on the bands, but they do. And this is really, in my mind, a really, really good proof of the standard model of cosmology, of hot Big Bang cosmology, which is what predicts the BBN measurements. So it's really cool to see that Big Bang nucleosynthesis and CMB measurements really align for this value of NF and omega B. So it's pretty cool. And these are the bounds that we have on N effective. There have been some minor improvements since then, but these are the two main bounds that we can consider. And now I want to move on to the constraints we have on the sum of neutrino masses. Now, if I was to show all of them, I would have about 20 numbers here on the slides. So I'm just focusing on five of them that I think are very interesting, very relevant right now. But there is a complete list of bounds in the Review for Particle Physics, or the BPG, that is maintained by Liz Gorg and Lucia Verda. And this contains all the bounds. It's updated every year. It's really worth reading if you want to see all of the neutrino bounds, and there's very cool explanations of what is happening. But I want to focus on these 5 measurements. So in every case, I'm presenting the upper bound on the sum of neutrino masses. Now, when we use CMB, so polarization and temperature anisotropies, we get an upper bound of 0.24 electron volts. So this is the bound on the sum of neutrino masses. It's a pretty good bound. This is from 2018. Once we include BAO, so baryon acoustic oscillations from SDSS, this increases to decreases to 0.13, which is very cool. This is a result from 2020. Other things we can include are lensing, for example, CMB lensing from the Atacama Cosmology Telescope. If we look at CMB coming from Planck 2018 and CMB lensing, so when I say CMB here, it's just temperature and polarization. Once we add in lensing from ACT, we get a bound of 0.12. So all of these are still consistent with both normal hierarchy and inverted hierarchy. Just a reminder that normal hierarchy gives us a lower bound of 0.06 electron volts. Inverted hierarchy gives us a theoretical lower bound of 0.1 electron volts. These are from particle physics. These are theoretical bounds. Then we can look at the very interesting combination of using CMB physics, so CMB temperature and polarization. From Planck, we can use baryon acoustic oscillations from SDSS, the Sloan Digital Sky Survey, and Lyman alpha from EBOS. This is a paper that was released in 2019. And they found an upper bound on some of neutrino masses of 0.087 electron volts, which is below the inverted hierarchy bound. And then the most recent bound that we have just this month is from Planck plus ACT lensing. So lensing from ACT, Planck, and BAO from DESI, which just released its first results. There we get an upper bound on the neutrino masses of 0.072 electron volts. Key thing to take away here is that the later bounds, including BOS, Lyman alpha, and BAO, are actually in slight tension with the inverted hierarchy scenario, which means from a cosmological point of view, we are pushing to beyond the inverted hierarchy. So cosmology is kind of disfavoring inverted hierarchy over normal hierarchy. This is very, very cool. And the fact that we have these now from different experiments is highly robust, because now we have Lyman alpha with EBOS, we have BAO DESI, which is also going to include Lyman alpha, but we can really see that all of these different bounds are coming together to really kind of disfavor inverted hierarchy. Again, a big caveat that all of these bounds are assuming lambda CDM, so standard cosmology. You could relax all of these bounds if, for an example, you change the dark energy equation of state, or if you change dark matter interactions, you can affect all of these different bounds. So again, this really is assuming lambda CDM, which is what I want to assume throughout this talk. But you could relax these bounds somewhat by changing cosmological model. So we're at a stage in cosmology where we have very good bounds on N effective, which are compatible with our theoretical predictions, and we have extremely precise bounds on the sum of neutrino masses. But this is not the end of the game. We're expecting that things are going to improve in the next few years as we get more and more precise data. So there are more experiments measuring the CMB beyond Planck, Atacama Cosmology Telescope, South Pole Telescope. There are more experiments. And there are more things in terms of large-scale structure of the universe and measuring the matter-power spectrum. In terms of the cosmic microwave background radiation, the next big step is going to be CMB stage 4. CMB stage 4 is going to be a combination of many ground-based detectors, and it is considered the next stage for CMB physics. Then we're going to have space-based experiments like LightBird. LightBird is a mission that is optimized to measure the B-mode polarization of the CMB, and it has been approved by the Japanese Space Agency. It is going to launch within the next 10 to 20 years. So LightBird is something that is going to happen. It has been funded, and it is going to try to measure the B-mode polarization of the CMB. In terms of large-scale structure experiments measuring the matter-power spectrum, we already have a lot of experiments that have started taking data in the last 2 years, and more are going to join in the future. So we have DESI, the dark energy spectroscopic instrument, which is going to provide incredibly precise BAO measurements. We had the first data release this month, which is very, very cool. Obviously, Euclid launched last year. Euclid is going to do galaxy survey. It's going to measure galaxy clustering and cosmic shear, so it can get constraints of the matter-power spectrum at slightly smaller scales. And ideally, within the next 10 years, we're going to have SKA, the Square Kilometre Array, which is going to be the largest network of radio telescopes in the world. SKA is ideally going to measure cosmic shear, galaxy clustering, and it's going to hopefully get a map of neutral hydrogen. This means that all of these things are going to give us constraints on the matter-power spectrum, and this is in turn going to improve our constraints on the sum of neutrino masses and on ineffective. And I just want to show you how much we expect this to improve in the coming years. So I want to very, very briefly talk about a paper we put out in 2018, which was kind of a catalogue of what we hope to do for neutrino physics in terms of measuring the neutrino mass in the next 10 years. So this was 6 years ago, so we're kind of halfway through our prediction. But let's just go through and see what we have here. So what you can see here in the figure on the right is a summary of a lot of different runs. There's like 135 data points here, so I'm going to break it down. So what we're looking at here is different combinations of CMB missions and a large-scale structure mission. And what we want to see is the constraining power on the sum of neutrino masses. So each of the subpanel corresponds to a different CMB experiment, and each column in the subpanel corresponds to CMB plus something, for example, the DESI, Euclid. So really each panel shows you how different CMB missions are going to behave in alone or in combination with other experiments. And the different shapes here denote the different cosmological models. So this means that, for an example, if you want to know what Planck alone does, you focus on the bottom left panel here. If you want to know what Lightbird is going to do, you go to top left panel. If you want to know something like Pico or Core, which I didn't discuss, there are the different panels here. But let's just focus on the bottom left. So let's focus on, for an example, using Planck. So bottom left panel here, the first column is going to be just Planck. The second column is Planck plus DESI. The third column is Planck plus Euclid. The fourth column is Planck plus Euclid plus SKA. And the last column is assuming we get some independent measurement of the depth to reionization, which would actually help improve constraints, but I don't want to focus on that right now. The dashed lines you can see in the background correspond to the 1 to 5 sigma thresholds for detection, where we have assumed the minimal normal hierarchy. So we assume that the total mass is going to be 0.06 electron volts. So then we look at how sensitive we are to this normal hierarchy. So focusing on the bottom left and just focusing on the circles, which is the case of lambda CDM, we can see that with CMB, we're at about 0.1, 0.2, which is compatible with the results I've already shown you. When we go to CMB, so we go to Planck plus DESI, our prediction that we made in 2018 was that Planck plus DESI was going to reach a sensitivity of around just enough to slightly move between 1 and 2 sigma of the normal hierarchy. And this is getting more and more precise as we add more experiments. So for an example, the combination that is going to happen of Lightbird plus Euclid is going to already push us to potentially a 4 sigma detection of the total neutrino mass. One thing we really wanted to highlight here is that there is great complementarity between ground-based and space-based missions. So for an example, if we take CMB stage 4, which is going to happen, and Lightbird, which is going to happen, and Euclid, which is already taking data, we should already have enough sensitivity to be able to measure normal hierarchy within 5 sigma. So what we really wanted to show here is that there is a high chance that cosmology is going to measure the sum of neutrino masses within the next few years. So when we put this out, we said like within the next 10, 15 years, we might measure the sum of neutrino masses. And now we're getting there. Once we get data from Euclid and more precise data from DESI, once we get SKA joining the game as well and Lightbird joining the game, we're really going to get incredibly precise constraints on the sum of neutrino masses. So the takeaway of this slide here, of this analysis that we did, is that it really is likely that cosmology is going to get incredibly precise measurements of the sum of neutrino masses very, very soon. But there are still some open questions, some of which are going to be discussed in other talks in this conference. One question is, do we have good control of the nonlinearities? I mentioned early on in the talk that when we do neutrino physics, we do need to account for the nonlinearities in the matter power spectrum. This is something that there are some bias effects, there are some things that we need to take into account. There are a lot of people working on making sure we have very good control of the nonlinearities. Another very cool question that I didn't discuss here, I mentioned that a lot of our bounds are directly dependent on the model that we are considering. And I did mention that there is this kind of degeneracy between n effective and the Hubble parameter, which comes from reabsorbing the background effects. So then the big question is, can we use neutrinos to solve the cosmological tensions? This is something that we'll be discussing in other talks. Just to give you a teaser, if you look at this figure on the right, I'm showing the bounds on the sum of neutrino masses obtained by Planck plus BAO, and the case where we vary n effective, so it constraints on neutrino masses n effective. We also have the Hubble parameter and sigma 8, and you can see that there is a really big interplay between the Hubble parameter, sigma 8, and the sum of neutrino masses and n effective, but I'm not going to talk about the cosmological tensions. Another question we need to ask is, are there any issues related to the priors? When we do these neutrino bounds, should we assume normal hierarchy? Should we assume inverted hierarchy? Should we assume no lower theoretical bound on the sum of neutrino masses? Because we're doing Bayesian statistics here, the priors that we put, so with the assumptions that we put on how our data is distributed, are going to slightly impact our results. So there is a very interesting question of how much we should pay attention to, or how much we should consider prior knowledge when we do these measurements, and this really does impact the results slightly. Something I didn't have time to discuss here, but it is very interesting to bear in mind that there are potential prior issues when showing these figures. And the very interesting question that I love asking is what happens if we never measure the sum of neutrino masses from cosmology? So what happens if we disfavor inverted hierarchy, we gradually push the bounds lower, and we disfavor normal hierarchy? What happens if we just keep pushing this bound lower and lower but never get a measurement? And that's a very cool question that we're also going to discuss in the conference, but I think it's really interesting because it opens up a lot of possibilities for new physics if cosmology never measures the sum of neutrino masses. Okay, bringing everything together, I just want to wrap up here. Neutrinos play a key role throughout the history of the universe. They act as radiation in the early universe and matter in the late universe, which means they contribute at different stages to the evolution of the universe. This means that cosmology is sensitive to neutrino properties, and specifically we can constrain two things with cosmology: the number of neutrinos and the overall mass of neutrinos. Current constraints on the number of neutrinos match theoretical predictions and provide very good alignment between Big Bang nucleosynthesis and CMB measurements, and it's really a good proof that we're on the right track with a lot of our cosmological models. The current bounds we have on the total sum of neutrino masses slightly disfavor inverted hierarchy, and it does seem like we're going to get more precise measurements in the future. So two takeaways here: cosmology really does provide many avenues to measure both the number and the masses of neutrinos, and there are exciting years ahead for neutrino physics. We can expect that within the next 10-15 years, cosmology really is going to give us a lot more information about neutrinos. So stay tuned, the future is bright. So with that, let me thank you all for listening. If you want to ask questions, feel free to reach out on Mattermost and of course in the discussion session of the conference, and you can always email me. So thank you everyone for listening.